channel Sri Guru Datta Education. In this video we are going to discuss Modern Physics Unit 1 Atomic Spectra and Models, Inadequacy of Classical Physics. Chapter 1 Brief Review of Blackbody Radiation. Image of a blackbody. What is a blackbody? It is a cubical structure which is fully black. A short answer type question is given here. We are going to answer a short answer question in this way if it is asked in your exam. Give a brief description of blackbody radiation. A perfect blackbody is one which absorbs all the radiations of all wavelengths incident on it. That means a perfect blackbody absorbs all the radiations with any number of wavelengths incident on it. It can neither reflect nor transmit any radiation. That means a perfect blackbody never reflects, never transmits. It appears black whatever be the color of incident radiation. It just appears black. It will be like a blackbody. It will be black itself. When any color of light, whether it is a white, red, Vibgyor colors incident on the blackbody, it never changes. It appears always black. So a perfectly black body is a good absorber as well as a good radiator. When heated to suitable high temperature, it emits radiation of all wavelengths. That means when starting it has absorbed, when we heat it, it will emit all the wavelengths of all radiations. As the radiation emitted by blackbody is rich in maximum possible wavelengths, they are known as full radiation or total radiation. So the radiation emitted by blackbody is rich and with maximum possible elements. That means we'll get full wavelength, so that it is said to be full radiation or total radiation. The wavelength of emitted radiation by a blackbody depends only on its temperature and is independent of the material of the body. That means it depends only on the temperature. How much we heat, that much the radiation will be emitted. It is independent of the material of the body. It doesn't, for example, I am taking a kg blackbody so that I will get this much amount of wavelength emitted. No, it doesn't show in that way. It depends just how much we heat, that much radiation will be emitted. There is no perfect blackbody. According to physics, there is no perfect blackbody. The nearest approach is lamp black or platinum black. Lamp black or platinum black is said to be a blackbody. These are capable of absorbing the visible and a part of near infrared radiation. These are just capable of visible region and infrared radiation. Here we can see a essay answer type question. Explain in detail about blackbody radiation. A blackbody is a body which absorbs radiation of all wavelengths incident upon it. It neither reflects nor transmits any of the incident radiation and therefore appears black, whatever be the color of incident radiation. A blackbody is an idealized object which absorbs and emits all frequencies. Classical physics is used to derive an equation which describes the intensity of blackbody radiation as a function of frequency for fixed temperature is known as Rayleigh-Jean's law. At fixed temperature of heating, we'll get all the radiation emitted. So that this process is known as Rayleigh-Jean's law. Consider a blackbody of hollow object with very small hole at its interior. So it is a hollow object which has a small hole interior inside it. When a radiation is set to fall on the hole, it gets trapped by undergoing many reflections in the cavity walls. Here we can see how many reflections a light is taking inside the hole of a blackbody. The cavity walls continuously emit and absorb until the radiation is absorbed. So the cavity walls continuously emit and absorb until the radiation is absorbed by what? Black body. The hole, inside the hole, the cavity walls continuously emit and absorb until the radiation is absorbed by the total black body. The black body radiation can be sampled only by measuring the emerging output from the hole in the cavity. That means it can be a black body radiation can be sampled only by measuring the emerging output from the hole. From the hole itself, it absorbs all the wavelengths, so that by checking the hole we can know the total output. The amount of radiation of a black body is high at high temperatures, hot. For example, I am heating it, it is hot temperature, and its spectrum is peak at high frequencies. When I am heating it, its spectrum is high, the peak is high. When I am cooling it, the peak is low. Here we can see the spectra of a black body in a graphical way. When it is 1800 Kelvin, we can see a high peak. When it is 1200 Kelvin, the peak is low. Here, this is the subtopic. You need to write as a subheading in your long answer. Ultraviolet catastrophe. Lord Rayleigh and James Jeans in 19th century proposed a law on the calculations for the spectrum of the black body. So, as we know, Rayleigh-Jeans law is given by these two scientists, Lord Rayleigh and James Jeans. In 19th century, they proposed a calculation for the spectrum of black body. In this law, the walls of cavity at absolute temperature T are considered as perfect reflectors, and the radiation as a series of standing electromagnetic waves. In this law, in this Rayleigh-Jeans law, it is said the walls of cavity at absolute temperature T are considered as perfect reflectors, and the radiation as a series of standing EM waves. Here EM waves are electromagnetic waves. By the radiation as a series of standing electromagnetic waves, we can know the absolute temperature in the walls of cavity. The condition for standing waves in the cavity with a node at each reflecting surface is, there are nodes and antinodes forming in electromagnetic waves, so that the condition for standing waves is given as path length from wall to wall equal to n lambda. In a cavity, the number of independent standing waves per unit volume density of standing wave is expressed as G of V dV equal to 8 pi V square dV by C cube. I repeat, G of V dV equal to 8 pi V square dV by C cube. Where in this formula, V equal to frequency of light, C velocity of light. Here V is inversely proportional to 1 by lambda and inversely proportional to number of possible standing waves. The standing waves in a cavity possess 2 degrees of freedom, that is mode of energy, as they are generated by oscillating electric charge in the cavity walls. Here the standing waves in a cavity possess 2 degrees of freedom, as they are generated by oscillating electric charge in the cavity walls. Hence, in classical physics, the average energy per standing wave is given by epsilon E equal to 2 into average energy per degree of freedom of an entity equal to the value of average energy per degree of freedom of an entity is half kT. So, epsilon equal to 2 into half kT. where K, Boltzmann constant, equal to 1.381 into 10 to the power of minus 23 joule per Kelvin. T, temperature at thermal equilibrium. Then the Rayleigh-Jeans formula for the energy distribution of black body, or the total energy U of V dV per unit volume between V and V plus dV, is expressed as. Here he is telling the Rayleigh-Jeans formula for the energy distribution of black body from V to V plus dV. V is the initial one, V plus dV is the final one. By the total energy is given by U of V dV. As V tends to infinity, the spectrum reaches to ultraviolet end and U of V dV tends to infinity. But practically, as V tends to infinity, U of V dV equal to 0, which is contradictory to the original value. This discrepancy is considered as ultraviolet catastrophe. When V tends to infinity, U of V dV equal to 0 according to the original value. But he is telling us V tends to infinity, U of V dV tends to infinity. So this discrepancy is considered as ultraviolet catastrophe. Planck radiation formula. This is the subheading, another subheading of essay answer type, and here we can see the scientist Planck. In order to explain the experimentally observed distribution of energy in the spectrum of black body. Planck radiation. Planck has given one statement experimentally about spectrum of black body. Planck in 1900 suggested a theory that the correct results can be obtained if the energy of oscillating electrons is taken as discrete rather than continuous. He is telling, don't take it as a discrete, take it as continuous. Continuous, the flow of electrons in the light is continuous. Till now we took discrete, that means sometimes the flow of electrons will be there, sometimes it may not be. He is telling to take it as continuous so that we may get the exact value. According to Planck, the energy density of black body radiation is expressed as U of V dV equal to 8 pi h by c cube into V cube dV by e to the power of h nu by kt minus 1, where h, Planck's constant, equal to 6.626 into 10 to the power of minus 34 joule per second. At high frequencies, h nu is double greater than kt. So, E h nu by kt tends to infinity, then U of V dV tends to 0. Hence, avoiding ultraviolet catastrophe at low frequencies, h nu is double lesser than kt. Then, E h nu per kt equal to 1 plus h nu by kt plus h nu by kt whole square by 2 factorial plus so on. Then in the next step, we are getting 1 by e to the power of h nu by kt minus 1 equal to 1 by 1 plus h nu by kt minus 1. This is similarly equal to kt by h nu. Then U of V dV similarly equal to 8 pi h by c cube into V cube into kt by h nu into dV is greater than or equal to 8 pi kt by c cube into V square dV, which is referred as Rayleigh-Jeans formula. According to Planck, instead of possible energy of continuous distribution, specific energy exists in the cavity walls, which is expressed as epsilon n equal to n into h nu, where n equal to 0, 1, 2, so on. Thus the average energy per standing waves is given by epsilon equal to h nu by e to the power of h nu by kt minus 1. Hence, in classical physics, the standing waves are responsible to transfer the energy in the cavity walls at a quanta of h nu. So that the standing waves are responsible to transfer the energy in the cavity walls at a quanta of h nu. That means we should take the quanta of h nu energy inside the cavity walls. Where are the cavity walls? Inside the hole. Where is a hole? Inside a black body. So that we need to take the quanta of h nu inside the hole of cavity walls in a black body. Thank you. If you like my presentation or video, please like, share and subscribe to our channel for upcoming videos. Please tap on to the bell icon. Thank you.